Hey folks, this is Captain Jones here to talk to you about something called privilege. This will be the first of two lessons on an operating system, kind of what that is a little bit, and how certain parts of the LC3 architecture support an operating system. So our goals for today are going to be to describe the purpose and benefits of an operating system, why that's useful to us, and describe what it means for something to have privilege, and also how the LC3 implements that. And so along the way, we're going to discuss things like the memory map, the processor status register, and system calls. And by the end of this lesson, you should be able to describe how user programs are supposed to interact with the hardware on the LC3, and what is the name of the violation that occurs if they attempt to sort of try to circumvent that process. So let's get started. In this unit, we are going to talk a lot about how to control inputs and outputs. So we focus the last unit primarily on sort of the processing, and you could argue a little bit of the control unit. And then we're going to ask, okay, how do we actually use these to talk to real input and output devices that are useful? And so far we have assumed that our programs have kind of full reign of the memory. We could make the naive assumption that our processors or our programs have full reign of the input and output devices, but that actually ends up, we run into some problems. If you can imagine, I've got a program here that has the ability to just read all the inputs. It can do anything it wants with the outputs. It can halt the processor at will. Then there are potentially some issues with that. If there are multiple programs running, or we have potentially some malicious code that's running on our program. So without an operating system, we have you could imagine almost a little sandwich that looks like this, where the user code interacts directly with the hardware, that ends up being less than ideal for a couple of reasons. Number one is that we want to be able to sort of encapsulate or sort of put a little abstract interface to that hardware, because number one, this could be sort of like a library routine, in the sense that my programs, if it doesn't know how to read the inputs, then exactly how the inputs get read could potentially change from computer to computer, and the programs don't necessarily need to change, and the programmer doesn't necessarily need to know all the low-level details about how to interact with the hardware. So if that's sort of behind a function call or something like that, then that can actually make programming easier. Secondly, this note here is looking at a little messed up. It should say that it controls access. So it's I mentioned earlier that if there's like a malicious program running on my computer, then I don't necessarily want that program to be able to access all kinds of hardware stuff. So at least in that scenario, and in others, it's helpful to have a little layer in between the user program and the hardware that helps control access. And if nothing else, just make sure that user programs aren't trying to send bad data to an output device, or like control a motor to a position where they're going to actually cause mechanical damage or something like that. And I've got a little note here. When we say hardware, in this class, we're going to primarily that's going to refer to our input-output devices, our keyboard and our display. But in a larger operating system, that refers to all kinds of hardware, including network adapters, the actual memory interface. Operating systems are typically responsible for creating the file system on a computer. So there's lots of different ways in which we want the operating system to kind of manage our access to the hardware. And so when we have the operating system in place, instead of this program having full control over the whole computer, instead that program, if it wants inputs to be read, if it wants outputs to be changed, if it wants the processor to be halted, it has to request that from the operating system. And so the programs themselves can't do anything to affect our hardware. They can make requests, and then it's up to the operating system to decide if it wants to fulfill those requests and in what way. And so these requests are generically called system calls. We've actually seen a bunch so far. So when we want to get a character or show a character or something like that, we've used the trap instruction to do that for us. And we sort of assumed up to this point that there's other code somewhere that's doing that for us, and that is the operating system in this case. So the trap 23 is the request that's made to the operating system in order to get a character from the keyboard. So the trap instruction is one example of our of the system call, and And so that occurs here in the instruction cycle. After we fetch an instruction, we decode it, then at some point in our sort of instruction cycle, we realize this is a trap instruction. And we'll look at in a future lesson how the execution of that instruction differs slightly from some of the other ones we've seen so far. And so then I got an example here of, well, actually, we'll come back to this in a sec, because this is using a term we haven't quite introduced yet. Okay, so let's talk about something called the memory map, which is this sort of diagram you can see here. This is the other way that the LC3 implements privilege. So we've sort of maybe assumed up to this point, that we had 65 kilobytes of memory, 0000 to FFFF. We might have thought to ourselves that, effectively we could fill the whole space with our user program. And some of you may have thought it was really strange that we started our programs at address 3000, and maybe this one made more sense. The reason is because we want to divide our memory into areas that have different responsibilities. So memory address is 3000 all the way up to FDFF would be the one right before this, is what's called user space. So that is the section of memory where actually all of our user programs will get stored and will get run. And you can see down here at the bottom that by convention, typically the stack pointer that we learned about previously starts at FDFF. That's why the address was in that lesson, and grows upward. So the USP here is the user stack pointer. This points to the top of the user stack that starts at the bottom of user space and grows upward towards user programs. The last section of memory, FE00 to FFFF, is called the I/O page. So this is the place where we will actually be able to control our hardware, read from the inputs or control the outputs. We'll see in a future lesson how we do that, and we want to make sure that space is not available to normal user programs. So we mark this part of the memory as privileged, and then we set aside the top of our memory map, 0000 to 2FFF, as system space. And when we make these system calls, when we execute these trap instructions, they're effectively cues to the processor to run some piece of code in system space, which is allowed to access the hardware down here at the bottom of the memory map. And just like user space has its own area for its stack, at the bottom of system space is a supervisor stack with SSP, the system or supervisor stack pointer that grows upward into system space. So our memory in actuality is sort of subdivided into really three broad categories, right? System space, user space, and the hardware page, and or the I/O page. And the system space and the I/O page are privileged, meaning only they can only be accessed by code that's running in system space. And all of the user programs that run here cannot directly access the I/O page. They can only make requests to access the I/O page, and those requests go through some program written in the system space. So the processor has two special registers that are stored in the I/O page that we'll see a lot of over the next few lessons. Number one is the PSR, processor status register, and so this is at location FFFC, so we can read and write the values as long as we have the right privilege by reading and writing from this memory location. And there are a couple of bit fields that are really important to us. Number one, at the very bottom, so bits 2, 1, and 0 are our condition codes. So if at all we need to sort of set or change the condition codes that come out of our ALU from the as the result of an operation, then we can read the lower bits of the processor status register. The most significant bit, so bit number 15 here, is called the privilege level, and by convention, if the privilege level is set to a 1, that means we're in user space, and if it's a 0, we're in the system space. And so here you can see if we are trying to access the processor status register, this register, which is in the I/O page, we're going to assume here that we don't have the privilege, then we get what's called an access control violation. We have some piece of code here, assumably running in user space, which is trying to directly access the I/O page, and it doesn't have the access for that. So that's an access control violation. If it wants this processor status register to change or get that value, then there would need to be some type of trap instruction, some system call that would allow it to do that. The second register that's in the I/O page that we'll mention right here is the MSR machine status register, and this is located at FFFE. It has one bit of interest, which is the most significant bit, bit 15. That's called the clock enable. So this bit is set when the device, the LC3 is turned on, and if at any point in the program it is cleared, then the processor halts. So this is what when we execute trap 25 to halt the processor. At some point in this system call, there's an instruction that clears this bit, and that's what halts the processor. Okay, so today we talked about the benefits of an operating system, which are number one, that it is able to encapsulate access to the hardware, and that does two things for us. One, it helps, it kind of makes accessing hardware more like a library routine. So we can write the programs to access the hardware once, and then future programmers don't necessarily need to concern themselves with the details of how to do that in the future. They can just make system calls in order to try to access that hardware. Number two, the operating system controls access to those hardware, so it can make sure that random programs aren't able to halt the processor without there being certain conditions in place. Normally it is just programs that are able to request, if they want anything to change in the hardware, they have to request that through a system call. The trap instruction is one example of that system call. And if ever a user program tries to access the hardware, without that system call, then we get an access control violation. And the way the LC3 implements these features are by, one, dividing the memory map into a couple of key spaces, namely system space, the user space, and the I/O page, and by marking the system space and the I/O page as being privileged memory. So the user space can't access those places in memory. The only way the processor in hardware allows that to happen is via the trap instruction. Inside the I/O page are two special registers: the processor status register and machine status register, and these can have a couple of bits that control very important things about the processor. Namely, bit 15 of the PSR is our privilege level, and if this privilege level is set to 1, that means we're in user space, and any attempt to access system space or I/O page results in an access control violation. And it's just in the processing of the trap instruction that we sort of move ourselves from an unprivileged to a privileged level. And when we start running code in system space, that's when the processor allows access to the hardware page. All right. In future lessons, we will look at how these trap instructions work, as well as how to actually interact with the hardware. Otherwise, that's all I got. I'll see you next time.